Welcome back to the deep dive. Our mission today is all about memory. Not, human memory, but machine memory. We're looking at how a deep learning model can process information that unfolds over time. So we're diving into architectures built for things like text, audio, code, anything that comes in variable lengths.
And we're pulling the curtain back on how sequence processing really works, drawing a lot from the material in the Stanford CS231n 10th anniversary course.
A great source.
It is. And what's really important to understand is that the material, it doesn't just jump straight into sequence models. It actually grounds us in the fundamentals first.
Which you have to do.
You have to. They start by wrapping up the core challenges of just training standard neural networks, things like weight setup, normalization before pivoting to the star of the show, recurrent neural networks, or RNNs.
And that initial groundwork is so essential, so let's not skip it. I mean, before you can even think about sequences, you have to get your training stable. The sources laid out this crucial checklist, basically the one-time setup you need to get right.
Right, choosing the activation function, pre-processing your data correctly.
Envisioning a good weight initialization,
Right.
Figuring out your normalization. Plus, they clarified little details, like how to scale dropout probabilities when you move from training to testing.
And this leads us to a really fascinating experiment that was cited, which addresses this seemingly simple but really critical question.
Which is?
Can normalization on its own fix the mess that happens when your weights are initialized badly?
Right. It's almost intuitive to think it would. You just shove the data back into a neat standardized box and everything's fine.
You'd think so.
The experiment they ran was beautiful in its simplicity. A toy setting, 2D input, a small two-layer network.
Yep, using RailU activation.
Yeah.
Just trying to learn a basic quadrant function.
So what was the verdict from the loss graphs?
Well, the graphs were tracking mean squared error loss over 1,000 epochs. And they delivered a very clear finding. You saw 4 lines.
Okay.
The blue line, which was bad in it with no normalization, just catastrophic. The network completely failed to learn anything.
Total failure.
Total failure. The red line, good in it with layer normalization, was the clear winner. Fastest convergence, lowest error. So layer norm, it dramatically reduced the error in all cases.
But this is the key takeaway, the part that really stuck with me.
Mm-hmm.
The performance gap between the good and bad initializations, it was still there, even when you applied layer norm to both of them.
Exactly. Normalization helped the bad in it a lot, but it didn't. It couldn't erase that fundamental disadvantage from the bad setup.
So it's not a magic bullet.
Not at all. It's a powerful tool, don't get me wrong. It controls the scale and distribution of activations while the network is running, so your signal doesn't, explode or vanish.
But it can't fix a bad trajectory.
Precisely. If your initial weights send your training process driving off a cliff, layer norm might give you a slightly smoother ride on the way down, but it's not going to pull you back onto the highway.
So if you're building these systems, you still have to get the basics right. Layer norm isn't a substitute for smart weight selection.
And the sources added a really vital nuance here, specific to this experiment.
Okay.
Layer norm worked particularly well in this quadrant function case because, and I'm quoting here, it does not change the quadrant of inputs.
So it preserved the geometry of the problem.
It preserved the underlying decision boundary the network needed to learn. That context is everything. Normalization is a strong tool, but you have to know how it interacts with the actual problem you're solving.
And of course, this is all before we even get to what they call training dynamics.
Right, babysitting the learning process.
I love that phrase. They showed this incredible grid, visualizing over 200 different training runs at once, tweaking things like batch size and dropout. It just reinforces that the initial setup is one thing, but the constant monitoring and tweaking, that's where the real work is.
That holistic view is what separates the beginners from the experts.
Speaking of experts, let's make that leap now. We've set up how to train a stable network for, say, a fixed size image.
Sure, or a data table.
But the real world is messy. How do we process a novel, or a 3-hour symphony, or a big block of code, things without a fixed length?
Well, standard networks just hit a wall there. They need a fixed size input. They have no memory.
So you need something new.
You need an architecture that operates sequentially and can sort of fold the past into the present. And that's exactly where recurrent neural networks come in.
Okay, so how does the basic architecture create that internal memory loop?
Let's use the simplest example from the source material.
Yeah.
A character-level language model. and it's just trained on the word hello.
Okay, so the vocabulary is tiny, just H-E-L-O.
That's it. The network moves one character at a time. So you feed it H, it goes into an input layer that affects a hidden layer, which then produces an output. So far, pretty standard stuff.
But the magic, the recurrence, that has to be in the hidden layer, right?
That is the entire innovation. The hidden layer, at any given time, let's call it time t, it receives two inputs.
Two?
Two. It gets the current character input, $6, and it gets the state of the hidden layer from the previous time step, head p.
Ah, so there it is. That hat T1 is the memory.
It is the network's short-term summary of everything it's seen so far. It's the memory.
So the entire history of the sequence gets compressed down into that one vector and then just folded back in.
That's exactly what the math describes.
Yeah.
The core equation is ed t1 plus t1.
Okay, break that down.
You have two pieces adding together. One part, all because t1 processes the new character. The other part processes the past memory.
Got it.
You combine them, squash them through a ton function to keep the values in check, and out comes your new updated memory state, $.
But if you're trying to encode a whole paragraph or even just a long sentence into one single vector at every step, how does it not instantly forget the first word by the time it gets to the last? It sounds like trying to hold a gallon of water in a thimble.
And you've just hit on the central critical limitation of the vanilla RNN.
The forgetting problem.
The forgetting problem.
Yeah.
That constant compression and overwriting means the influence of early inputs just decays really fast. It's the short-term memory problem, and it's what directly led to more complex models like LSTMs and GRUs, which we can get into.
Okay, but for now, let's just watch this basic mechanism work. We can see it in action during test time sampling. The model is like a one character at a time fortune teller.
It is. Once it's trained, you give it age. It spits out probabilities for the next character. In the example, it samples E with super high confidence, like 0.84.
And then that E.
That sampled E gets fed right back into the model as the next input.
So it's talking to itself.
It's talking to itself. The hidden state updates based on E, then it predicts old, then L again, then Ella. The entire sequence is generated one step at a time, completely dependent on the context it's maintaining in that hidden state.
And if you scale that up, moving from just predicting characters to predicting complex structures, the applications get impressive really fast.
Oh, incredibly fast. These models went from simple character prediction to handling very sophisticated language. The sources gave examples of code generation, where RNNs were producing long, syntactically plausible C code.
Which is so much more than just predicting the next word. You have to understand nested loops, scope, indentation.
The whole structure.
And that's the engine behind these huge industry tools now, isn't it? OpenAI Codex, GitHub Copilot, Cursor?
Exactly.
Yeah.
They are all built on these foundational principles, just scaled up to generate whole functions or classes.
But when you get these complex outputs, the question of interpretability becomes unavoidable. What are those hidden units actually learning? Are they just black boxes?
Or are they developing specific jobs? And that's where the findings from Karpathy, Johnson, and Feifei in 2016 were such a huge aha moment.
The interpretable cell.
The interpretable cells, yeah. They dove into these networks and found that individual nodes were actually specialized.
And the specialization is almost weirdly human-like.
It's startling. They found cells acting as specific structural detectors. For instance, they found a, quote, detection cell. It would literally turn on and stay on only when the network was inside quotation marks.
Wait, really? So it's developing its own internal punctuation parser?
It seems so. And it goes further. They found a line length tracking cell that was sensitive to its position on a line, so it's learning visual structure.
Wow.
In generated code, there was an if statement cell that knew when it was inside a conditional block.
My favorite was the cell that specifically turns on inside comments and quotes in code. So it knows the difference between executable code and just commentary.
It's like the network is building its own little utility belt. It's learning these high-level syntactic boundaries that go way beyond just predicting characters.
It really is. And this specialization, it kind of hints at a more complex idea of resource management.
Well, the source material references a related concept.
Yeah.
That the network can learn to choose to read from or write to specific memory addresses.
Okay, so it's not just updating one hidden state, it's learning to manage like separate pieces of long-term storage.
It's a suggestion that it's learning to actively decide which memories to retrieve and which to update.
That kind of selective control feels like a step towards something much more cognitive. But RNNs aren't just for text. They moved into multimodal tasks too.
Absolutely. The next logical step was to combine the spatial power of CNNs with the sequence power of RNNs. And the classic breakthrough here was image captioning.
Right. You take a static, fixed-size image, and you get a variable-length sequence, a sentence, as the output.
It's a really clever architectural blend. A CNN first processes the image, with its conv layers, max pool, FC layers. Its only job is to boil the whole image down to a single feature vector. Let's call it V.
And that vector V is the visual context for the RNN.
Precisely. The RNN's standard equation gets a little upgrade. It becomes Salter S Hopkins plus WA phi.
That third term.
That third term, 1AD, injects the visual data directly into the hidden state calculation at every single step. The RNN is grounded in what it sees.
So the network starts with a start token, uses that vector V to guide it, and then starts predicting words, man, throwing frisbee, until it hits an ND token.
And the early results from models like NeuralTalk 2 were stunning, generating accurate captions like, a cat is sitting on a tree branch.
Or two giraffes standing in a grassy field. These are novel sentences, right? It's not just pulling them from a database.
It's generating them from scratch.
Hmm.
But the failure cases, that's where you learn the most.
That's always where you learn the most.
They absolutely are. The model really struggles when the action is subtle or unusual. We saw these examples where it generates a perfectly plausible sentence that's just completely wrong about the image.
You mean like the woman doing a handstand by a lake being captioned as a woman is holding a cat in her hand?
Exactly. Or a baseball player diving to catch a ball being described as throwing a ball.
So it gets the nouns right. Woman, cat, player, ball. But it completely whiffs on the verb, the actual action or relationship.
It does. It confidently produces a grammatically perfect sentence that is pure fiction.
That's almost more worrying than a random guess. It seems like the compounding error of predicting sequences, combined with ambiguity in that visual vector, just sends it off the rails.
That ambiguity is key, but this multimodal capability still showed so much promise. It led to even more complex stuff like visual question answering, or VQA.
Where you ask the model specific questions about the image?
And even visual dialogue, where you have a full conversation with it about the picture. You ask, what color is the mug? And then a follow-up, is the person smiling?
And it doesn't stop there. Vision, language, and navigation.
Right, in the physical world, a robot gets an instruction like, go up the stairs and turn left at the red door. It uses an RNN to encode that sentence, generates movements, and then updates its plan based on what it sees after each step. It's the ultimate test.
Okay, let's unpack all this. We've seen RNNs create this memory loop, lead to breakthroughs in generation and multimodal tasks. What are the key lessons we have to take away?
The biggest lesson is flexibility. RNNs gave us a template that could handle any length of sequence data, but as you pointed out, the vanilla ones have that fundamental forgetting problem.
Right. The sources are clear that simple RNNs, they generally don't work very well in practice.
Not on their own.
So the solution to the forgetting problem was what?
Selective memory. More complex versions, like long short-term memory networks, LSTMs, and newer models like Mamba, introduced internal gates.
Like little switches.
Exactly, like read, write, and forget switches to selectively pass only the relevant information forward. That solved the bottleneck.
And from an engineering perspective, how did they even manage to train these deep sequential systems?
The big technical problem wasn't just forward-looking memory, it was the backward flow of gradients during training. They called it backpropagation through time.
And the gradients would
They would either explode, get ridiculously large, or vanish, become basically zero.
And gradient clipping fixed one side of that, didn't it?
It did. Exploding gradients were managed with a very practical fix called gradient clipping. You just cap the maximum size of the gradient. It keeps training stable.
But the vanishing gradient problem?
That required the architectural fixes we just mentioned, like the gates inside an LSTM, to make sure the signal could actually travel back through all those time steps.
So it's clear that while RNNs showed us how to handle sequences, they needed a lot of extra engineering clipping, LSTMs, complex gates to really work.
A lot of scaffolding.
And the source material makes the point that the cutting edge is always moving. They say, better, simpler architectures are a hot topic of current research.
Which is the perfect summary. I mean, if LSTMs and Mamba gave us selective memory, allowing the network to filter what it keeps in its single hidden state, we have to ask the next question.
Which is?
What happens when the network doesn't rely on sequentially updating a single compressed hidden state at all?
You mean just abandoning the sequential loop entirely?
Precisely. What happens when we turn our attention to the relationship between all the elements in a sequence? Weighing all the words simultaneously, no matter how far apart they are, it raises a really important question.
Okay.
What happens when we move beyond recurrence and dive entirely into the dynamics of relationship? And that is where we find the next massive leap in deep learning, attention and the transformers.